So we continue. So last time we talked about this quantum tunneling and potential barrier problem. So today we will continue and finish this part of the discussion. So last time we tried to solve the Schrödinger equations for this potential barrier problem. Although it's complicated, but the textbooks and also the textbook already solved for us, and you need to check once in your lifetime that these are the solutions. And the transmission coefficient and reflection coefficient, the square of them, are given by these two results. Look horrible. As you'll see later that we have some more intuitive and approximation that are available to understand this physics. But if you sum of this r squared and t squared, you'll find that this is simply just 1. And this is not a coincidence. So you know very well that we have this particle conservation, and this actually reflects this kind of a conservation law of this particle flux. And well, so let's just analyze this r squared and t squared. This a, the little a here, represents the thickness or width of this potential barrier. So if a is actually very, very wide, then you have very flat and very wide range potential barrier. But if a is really, really small, you have a very narrow barrier. So how large or how small the a is will determine this transmission coefficient. So when a is thick enough, or kappa times a is actually much greater than 1, right? So then you have this approximation that this hyperbolic sine or sinh of this 2 kappa a is more or less this exponential function, e to the 2 kappa a divided by 2. So remember, hyperbolic sine, yes, e to the x minus e to the minus x divided by 2. Right, so, and later we'll see this approximation from this quantity, that 2 times kappa a, whether this is very large or very small, or what value of this 2 times kappa a. Okay, so in that regime, this when a is thick enough or kappa a is larger than 1, and this hyperbolic sine is given by this exponential function. So this t squared can be further reduced to this prefactor times exponential decay. Okay, so this is a very important hint for later approximations. So this is the exponential decay. And this is something like a prefactor, a constant prefactor. So the transmission coefficient is nothing but a constant prefactor times the exponential decay with increasing a. So you could think of a situation where this a is very large and this is very wide barrier. Of course, for a very wide barrier, the particle cannot easily penetrate through the barrier, right? So the thicker the barrier is, the harder the particle can penetrate. And that's explain why this t squared decay exponentially with increasing little a here. But the most important statement is this: even though this energy is less than V0, meaning this initial energy of incoming particle carry the energy that is less than this potential barrier. Okay, so even in this case where the classical particle simply just get a total reflection, and there's no chance that classical particle can actually penetrate into or out of this barrier in that case, right? So but in quantum mechanics, it is allowed. You can see that from this calculation that there's still a finite transmission coefficient, even though this energy is lower than this potential barrier, V0. And this phenomenon is called quantum tunneling, which I mentioned many, many times. So finally, you see the corresponding mathematics, right? So transmission coefficient squared is given by approximately the constant prefactor times the exponential decay, where this decay function is given by this exponent is given by this minus 4 times kappa times a. So even though this kappa a is larger than 1, but you can still find a finite transmission, or even though this energy is lower than V0. Okay, so this phenomenon is real, and we will come back to this quantum tunneling in just a moment. Okay, so but let's just look at the second remark, very important, and I've emphasized many, many times, which is the question: why is there a finite probability of finding a particle with a negative kinetic energy inside the barrier? So as indicated by this dot or dash line here inside the barrier, you can see that the solutions inside this barrier is still finite. Remember, this u of x inside the barrier is what? Some a times e to the kappa x plus b times e to the minus kappa x, right? So there's a finite wave function distribution of this particle, right? Like a probability distribution. Because this is non-zero, so the particle can in principle exist inside the barrier. But the question is, why is that? Why is this? Okay? Why can a particle live inside a barrier which has negative kinetic energy? So the kinetic energy is idea from the classical mechanics, right? So the amount of kinetic energy is the difference between the total energy and your potential energy. But in classical mechanics, we know that a Newtonian particle carry kinetic energy of 1/2 m times v squared, and the mass is positive, and velocity squared is always positive, and so there's no way that kinetic energy is negative. It's always positive. So what does it mean when the kinetic energy goes to negative value? What does that mean? It does not make any sense in classical mechanics, because the classical object cannot carry negative kinetic energy, right? But the quantum mechanics allow such, as I mentioned previously, so-called virtual state. So the virtual state is the state that defies or contradicts the classical concept of kinetic energy, which is precisely this negative kinetic energy state. Or sometimes, some books, some people call this classically forbidden region or forbidden state, which means that in classical mechanics it is not allowed, right? But quantum mechanically it is allowed. So the quantum mechanics actually in some sense overcome this classically forbidden state or the rules in classical world, okay? But then what is the reasoning behind this negative kinetic energy state? And we should have a reasoning or argument to support that even if the state actually is inconsistent with the classical mechanics, but in quantum mechanics it is okay. In what sense is it okay? Right? So this is the question that we need to answer. So as I pointed out earlier, that this answer to this question always is related to the Heisenberg uncertainty relation. So we could understand, if we really like to see this particle inside this barrier carrying negative energy state, and we have a trouble. The trouble is that we actually contradicts Heisenberg uncertainty relation. Okay? Or if we would like to satisfy the Heisenberg relations, and we contradict ourselves. Okay, so let's see how it goes. So this is the first most powerful argument, that we cannot defy or we cannot contradict Heisenberg uncertainty relations. So what does it say? So as we already learned, that this delta x times delta p must be greater than or equal to half of h bar. But let's just see that we really try to find out where this particle is, whether there is ever a particle live inside the barrier. So we would like to measure or detect this particle inside the barrier. So this detector or the machine or the equipment that we like to detect the particle should really has the very high accuracy in determining the position. The arrow bar of this experimental machine in determining the delta x in order to see the particle inside the barrier, delta x must be much smaller than 2 times a, the width of the barrier, right? So if you really like to localize this particle inside the barrier, the uncertainty along the x direction should be much smaller than the width of the barrier. Otherwise, you cannot tell whether there is really a particle inside the barrier or not. Is that okay? So your uncertainty in determining the position in the x direction must be much smaller than 2 times a. Great. So, but from this Heisenberg relation, you immediately see that this delta p, the uncertainty in determining the momentum of this particle inside the barrier should be much larger than this value, h bar over 2 times a. Okay, so approximately. So you don't care about this factor of 2 or 1/2. Great. So which means that in order to see, you need to really hit the particle inside the barrier by something else, by a photon, by electron, by whatever particle that's available to you, and you simply want to suppose there's a target here, so there's a particle somewhere here, and you really like to see this particle. Then you need to actually use some detector, where the detector actually there's some particles that's sent out from this detector, and this particle will hit the particle. So the photon or electrons are going to hit this target, and you're to see this particle. So this actually effectively gives rise to this delta p, because this is the momentum transfer between the particle from the detector and the target particle. All right? So you need to send in some particle to hit the target in order to really see this particle inside the barrier, but then it really generates the momentum transfer. But based on Heisenberg uncertainty relation, this momentum transfer, delta p, must be much greater than this value. And this effectively gives you an energy transfer. So again, the energy transfer is the energy difference between your incoming particle from the detector and your target particle. Okay, so this is the energy difference between the initial and final state. Okay, so and then this delta E based on this delta P could be estimated as follows, because E is given by P squared over 2n, right? So if you have a delta P, which is the momentum transfer, then this will actually generating this delta E, which is about this amount. Or this delta E is much bigger than this value, h bar squared over this a m a squared. So let me just summarize this. So in order to see this particle, the target, the magnitude of this negative energy, which is absolute value of E minus V0, which we call this h bar squared kappa squared divided by 2m, which is the magnitude of the negative kinetic energy. So you could actually use this relation to see that the magnitude of the negative kinetic energy must be much larger than this error bar uncertainty in energy, right? So this delta E can also be understood as the error bar in determining the energy. So your detector has all sorts of error bars. So in determining this position, momentum, and also energy. Okay? So in order to really identify this particle, the error bar in determining the energy of the particle or target should be much smaller than this magnitude of the kinetic energy. This is the same reason that we need to satisfy this requirement that the error bar in determining the position of the particle should be much smaller than the width of the barrier. Okay, so likewise, the error bar in determining the energy of your target should be much smaller than the magnitude of the negative energy, right? Because the particle carry the negative energy. Okay, so if your detector is sensitive enough, and it should resolve this magnitude of the negative energy, okay, and therefore the error bar in energy should not be very large, should be very, very small. So this is the condition that you could really very confidently say that there is a particle because I know the energy of the particle, right? So the error bar for this energy should be much smaller than the magnitude of the energy that the particle carries. But we know that this energy transfer of the error bar, delta E, is much larger than this value. So let's just continue with this inequality that delta E is much larger than this value. So you can actually link this inequality from the very left to the very right and use our definition for kappa, and immediately you get this inequality, which means that 2 kappa A must be much greater than 1. Okay, so this is the price to pay. If we really want to identify the particle, we have a very high sensitive measurement position, and we also need to have a sensitive enough detector to resolve this energy, negative energy. But the consequence is that this 2 times kappa times A must be much larger than 1. But what is the consequence of this? You could go back to this t square. If you look at this approximation, this t square, when this barrier is thick enough, this kappa times A is much larger than 1, so you get exponential decay, right? Okay, but this is precisely the price to pay if we really want to localize the particle inside the barrier and want to see or observe that particle, and this is the price to pay. So effectively, we need to be in that region where 2 times kappa times A is much larger than 1. But what is that limit telling us? Well, this region is telling us that this t squared is almost negligible because it's proportional to e to the minus 4 times kappa times A, right? When this kappa times A is much larger than 1, this exponential factor is really, really small. So it goes to 0. Okay? So what does it tell us? Well, it tells us that in order to see or observe this particle inside the barrier, then the transmission coefficient is almost gone. There's no transmission coefficient. But we know that there must be a transmission coefficient, right? And therefore, this really contradicts ourselves. It's really not our purpose. Our purpose is to see this quantum tunneling, but the price is really too high. Okay, the price to pay in order to see this particle is that we lost the transmission. We missed the transmission. There's no transmission. Okay, just because we need to localize the particle inside the barrier and the transmission coefficient 0. Okay, so and then this logic is not going to work because we know that there is a finite probability that the particle can penetrate into the barrier because t squared is finite, but if we really want to know this particle ever lives inside the barrier, then the price is that transmission coefficient 0. So we contradict ourselves. This is an inconsistent result or contradiction result. So the conclusion is that because of Heisenberg uncertainty relations, we cannot detect whether there is a particle ever live inside the barrier. One cannot tell whether there is really a particle inside this forbidden region. Okay, so this argument is very important, which is to argue that why is the fact that we cannot find the particle inside the potential barrier. What is the reasoning behind this? Well, let's take a short break. When we come back, I will provide you with the second calculation or argument to support that even if there is finite solutions inside the barrier, we cannot know about this. We have no knowledge about this because we cannot detect the existence of this particle in the virtual state. Okay? So you must be very, very clear when you think about this in your mind. The logic is really, really important. Okay? So everything is related to Heisenberg uncertainty relation. Okay, so let's take a short break. 这部分是需要花一点时间去理解的哈，那是比较烧脑的部分啊。请各位务必要动动脑，然后理解这个有点违反直观的量子力学啊。Good. So let's just look at the second, support. As I mentioned, the solution from the Schrödinger equation for this potential barrier problem, this inside the barrier, is given by this exponential function, right? Okay. So a much simpler argument to support that you cannot detect the particle inside the barrier, even if you know that mathematically the solution is finite, is that no flux can be detected. Okay, so as we already mentioned previously, that to detect the existence of particle flow, the flux, the probability flux, is a very convenient and powerful way. And remember this, the flux J of x is what is proportional to this quantity inside the bracket. Right, so, but this psi here inside the barrier is a pure real function in x, right? It's a pure real function of x. So for real function, if you take the complex conjugate of this real function, you don't change anything. So it is the same as before, right? As a result, if you simply just plug in the solutions, whatever the real function is, as long as it's the real function of x, this quantity exactly cancels. So when this quantity is 0, and the flux is also 0, right? So in other words, if you really want to detect the flux, you will be disappointed because flux is 0. Flux is 0. So what does it tell us? Well, this tells us that if you really want to detect the particle, and at least you cannot tell from measuring the flux. Okay, if you put a detector inside the barrier and just look whether this particle actually penetrates through this area where you count this flux, and you will be disappointed because there's no flux. Okay, so but how come? How come you know the solution is there, but there's no flux? Okay, solution is finite, but there is no flux. Okay, so this seemingly counterintuitive statement defines precisely the essence of virtual state. So the virtual state in quantum mechanics is precisely this. Okay, so solution is finite, but there's no flux. Okay, so you cannot say that since you don't detect the flux and nothing is inside the barrier, no, there's something inside the barrier, but you don't know. So that's the answer. Something inside the barrier, but you have no way to know it. So that's the correct interpretation based on quantum mechanics. It sounds strange and weird, counterintuitive, but, well, this is the thing that we need to accept. Okay? So again, based on this Heisenberg principle, there's a fundamental limitation in quantum mechanics which limits our knowledge in knowing such a virtual state. So the virtual state is non-zero state, okay? But practically, you cannot detect anything non-zero from the virtual state. So that's the very contradicting statement. But we cannot say that the particle is absent in the barrier. But if you do so, then you get a bigger trouble, because if the particle is missing, if there's no, suppose there's nothing, just empty inside the barrier. Okay, since you cannot detect, so you say that there's no virtual state, nothing is there. Okay, then you have a bigger trouble. Because how do you explain this thing? Okay, the particle hit this barrier and suddenly it disappears and then it reappears later on the other side of the barrier. Okay, so this violates the particle number conservation, right? It's kind of a jump or discontinuity between inside and outside of barrier. Okay, so we must admit and accept that this is a very peculiar state called the quantum virtual state must be there. But practically, we have no access to that state. Okay, and this is really physical, because if you keep changing the width of the barrier to narrow and narrow, right? And for sure, at the end of the day, you know that the particle is really continuously passing through the barrier. So you could actually continuously shrink this barrier width to almost zero width. Then the particles really penetrate. You don't need this virtual state. You can also make this wider and wider barrier, so there is a less and less probability that the particle can tunnel, and at the end of the day, in this infinite width limit of the barrier, the particle just gets total reflection. In both cases, these results are consistent with our intuition and classical mechanics. But at the finite width situation, there's this very weird and strange result that we need to admit this quantum virtual state inside the barrier, and we don't have any way to know it. But you need to admit that it's there. Okay, so it's not just a hypothetical or just a kind of artificial, but it's real because, as we'll just see in just a moment, that this is the foundation of the STM technology. And the STM is a widely used experimental technique to probe this material at the atomic level. So it resolves this surface of any material in Armstrong, that short distance, short range. Okay, so we will come back to this STM in just a moment. So any questions so far? Okay, so I offer you two explanations regarding this virtual state inside the barrier. Okay, so by now you should not be too surprised that this is really counterintuitive. Good. So let's just look at some approximation which could give rise to some very simple results regarding the transmission coefficient called WKB approximation. So WKB stands for the three physicists called Wenzel, Kramers, and Bernoulli. So they try to simplify this solution with tunneling barrier problem and developed this approximated form called WKD approximation. So this approximation is based on this observation that this t squared is, again, a prefactor, a constant prefactor, times this e to the minus 4 kappa a. And we know that this t squared is really sensitive to the width of the barrier. A, because kappa A is this, right? Okay, so because this is exponential function, so when a change a little bit, this exponential function change a lot. Okay, so this exponential function is really sensitive function. Okay, so a very small change in a will lead to a very large change in exponential decay function, which means that this t squared or t is really sensitive to this width of the barrier. But we know that the square-like barrier is just an ideal or toy model, because this kind of a sharp edge of barrier never exists in practice. In real world, it is a very smooth kind of a bump-like barrier, like this. Okay. So, but when this transmission coefficient is small enough, then we could actually make some approximations to deal with this more general shape of potential barrier. Because we already know the solution in this, say, small transmission regime, that this t squared is given by the constant times e to the minus 4 kappa a. So, and this is the starting point for the square-like barrier in the weak tunneling limit. Okay, so WKB developed the approximation based on this observation that the general shape of the barrier could be decomposed into many little squares or rectangle like this. You simply just connect all this little rectangle, and then you approximately reproduce this general bump shape barrier. Of course, there's some zigzag, right? But this doesn't matter too much, because when you really decompose this barrier in terms of almost infinite number of rectangles, this kind of the zigzag, boundary will become very smooth if you keep meshing this barrier with more rectangles, and you got a very smoothly varying potential. So then you could consider the case where the particle hit the barrier like this, just like this single barrier. So WKB developed this approximation based on this kind of meshing of this general shape of potential barrier in terms of a little squares or little rectangle. And you notice that this 2 points on the left and right side of the barrier are this classical turning point, where classically, the particle, when it hits the turning point, will actually reflect back, right? Or that way. So each little rectangle, we can attach the transmission coefficient for that little square or little rectangle, and this total transmission is given by the product of all those individual TIs or TNs. And this is approximation, of course, but this approximation is reasonable in a small tunneling regime, that we could approximately just take the summation over the little slice of a barrier in the logarithmic fashion. Okay, so if you take the log of this t squared, you can separate this constant from this exponential decay, right? Like this. So if you take the log on both sides of this form, you get this constant minus this 4 kappa a, and you could simply just combine this 2 kappa and this 2a together. And you know that the width of the barrier is 2a, so you can simply just further decompose this 2 kappa times 2a in terms of many little pieces of the log t slice square, right? You sum over all the slices of the little rectangle, and this is precisely this approximation is telling us that this is given by -2 times this kappa at any given small rectangle and times there's delta xn, and delta xn is given by this, the width of this little slice. You simply just sum over all these logs of the Tn square over this little slice of the rectangle, and you could approximately find out this total transmission for this general shape of barrier. T1 square times T2 square Tn square. And we can actually calculate this WKB approximated form of T square. So log of T square, which is total transmission in the small slice limit, which is -2 times integral over the barrier, which is the smooth varying barrier, and this average value of the kappa for each slice is given by this square root of 2m v of x minus e divided by h bar square. All right? So by summing over this average kappa for little slice rectangle times this distance delta x, which is simply just the integration over the x, and this is what kappa, and this is delta x, and this is summation over n. Okay, so, but of course this is just approximation up to some constant. And this constant is nothing but the prefactor in the original form here, so we could just expand this integral and write down this WKB approximation, which is this, right? And C is this prefactor that's just mentioned, right? So for a general shape of potential barrier, you could use this WKB approximation. But of course, this approximation has limits. So this limitation is this. So this approximation is more accurate for a smoothly varying potential. And also, but this is less accurate when this energy is close to the turning point, close to V of x, because there kappa times A is what? Is really, really small. Because kappa, remember, is this value, right? So when V is very close to E, then this square root is almost 0. So this kappa times A is almost 0, and this violates the starting point that we have, right? So when transmission coefficient is small, this kappa times A must be very large. Okay, so this WKB approximation works only in this region, in the weak tunneling region, where this kappa times A is much larger than 1. So of course, when this barrier profile hits this turning point, that's nearby the turning point, this WKB breaks down. But that's just a tiny little region of the whole smooth varying potential. So that really comes back to this assumption that this WKB works for smoothly varying potential. So if you have a very widely distributed, very smooth potential, and this WKB works, even though that this approximation is not accurate just near the turning point. But that doesn't matter, because this just constitutes a just tiny little bit error bar when you do the summation. Okay, but you have the whole range of the potential profile that WKB works. Okay, but of course, if you have this kind of very sharp potential barrier like a spike or like a delta peak, of course WKB doesn't work, because this turning point, arrow bars actually near the turning point is actually constitute a very large portion of the whole summation. Okay, and so this only works in this type of very smoothly varying potential. Great. So let's take a short break. When we come back, we will final remark regarding to this experimental applications of this quantum tunneling phenomena. Okay, so let's just look at the very simple two examples of quantum tunneling effect. So one example is the so-called co-emission, and this is the application of quantum tunneling for a metal. So the electrons in the metal could be removed from the metal if you simply apply a voltage bias like this. So here is the cartoon picture of a metal, a piece of metal, even at room temperature. So suppose the, say, electrons populated up to, say, some energy level at chemical potential, and this is the other side of your sample or insulator, something like that, and with a potential barrier like this, with the barrier height W, and this is a step like a potential barrier, right? So if this is insulator and this is a metal, so the electron cannot get out. But if you apply a voltage across the x direction like this, so the potential profile, if I apply the electric field or voltage bias in the x direction, then this potential is no longer a flat function, right? So it's actually is bent downwards linearly, right, like this. So after you apply the voltage bias, you can get the linearly declining shape of a new potential barrier. So now, electron could, in principle, tunnel through this triangular shape of a tunneling barrier like this, right? Okay, good. So, and indeed, you could perform such experiments on the system. So you can use WKB to calculate this probability or transmission amplitude square of this quantum tunneling when you apply the voltage bias. And so electron can actually tunnel out of the metal through the other side of the barrier if you apply this bias voltage. And this is the WKB approximated form of this triangular shape of this tunneling barrier, right? So this is called co-emission because you could do it at room temperature, which is cold in the sense that you don't need to really apply high energy particles to actually introduce more energies or a large amount of energy. So this happens very easily at room temperature. You don't need to inject a huge amount of energy, to actually increase the temperature of the whole thing. So, and this is called a cold emission. So compared to the high energy injection, this is happening at a very cold temperature, so called cold emission. Okay, so the second example is the more well known, which is the STM, scanning tunneling microscope. So this is the equipment that allows us to really probe the atomic surface of your materials and in a very accurate way without much effort and damage. Okay, so this is called this metal tip of the STM, and usually this is a tungsten tip. Okay, and you know that this electron can actually move out of the tip or go between tip and the surface if you apply voltage bias, just similar to this co-emission. Okay, suppose this is also another piece of material. You could actually apply the voltage difference between your sample and STM tip. So effectively, this vacuum or the air in between this STM tip and the surface is precisely the tunneling barrier. You can consider that the electrons is injected, say, from the tip to the surface through this tunneling barrier. Okay, so if you don't apply the voltage bias, electrons cannot move. But if you do apply a very a small amount of voltage bias, like 10 electron volts. It's very, very small. And the distance between the tip and the surface can be as small as how much? It's 5 angstrom. And then you can actually move around this STM tip horizontally or vertically. And if there is some atoms distributed on the lattice, then you will see it. Because the electrons nearby these ions or atoms are distributed accordingly based on this periodic structure. So by STM tip, by moving around this STM tip, you could really see the signal as the intensity of your STM current. Okay? It's actually proportional to the density of states of those electrons that is just below the STM tip on the surface of this material, so you can actually measure the intensity, the STM intensity, which is proportional density of states of your electrons on the surface. So the STM signal represents how many electrons are there on the surface. So this is the very powerful way to resolve the spatial distribution of your charge and your atoms over a very short distance, like 55 angstrom. So your tip is about what? Is much wider, like can be 1,000 angstrom wide, but the tip should be very, very sharp in order to really resolve this very short distance on the surface. And distances as short as several atomic spacings, like, I don't know, say 10 to maybe 20 atoms. So even if your STM tip is very sharp, and you could really see atom by atom, you can really resolve this atomic structures at a single atom level. Single atomic. Okay, so compared to the previous electron microscope, one needs to really inject a very high energy of electrons, say maybe up to a few hundred or even 1,000 electron volts, to really bombard the surface that you want to see. Okay, so by such a high energy, you already of electrons that hit your surface, the surface already destroyed. So the STM is a very powerful way to use as little energy as possible for this electron at the tip of the STM to probe the surface without destroying the surface. Okay, so, and if you were doing experiments in the future, and the STM is a very popular experimental technique which allows us to see this charge density or atomic structures of many, many solid state materials. And the basic principle, as I said, is the quantum tunneling. So electron carry energy which will actually tunnel through this air to the other side. And the other side is the surface. And so you move around the tip and you can see this up and down of these atomic structures like this. So this is not a fantasy, and this is not a kind of a hypothesis, it is real. So the quantum tunneling effect is a real effect which can be measured in experiments. So now you can ask the same question, well, if the electron ever live in the air inside the barrier, of course, that's how you measure this STM signal. But if electrons are absent or suddenly disappear in the air, so how come you can have any signal in the STM? Right? So this is the proof, experimental proof, that the quantum tunneling effect is a real, measurable quantum mechanical effect. It's just that you don't know whether the electron is ever live in between. There's no way. But this effect is real. Okay, so I guess that's almost the end of the chapter 4, right? So except the harmonic oscillator problem. So let's just turn to the last section of this chapter, which is the, again, potential well problem, but it is a special type of potential well, which is the parabolic potential well, and we call this harmonic oscillator. So we already discussed this square-like potential well, right? Again, this is a very non-natural shape of this potential well, but the most natural shape of the potential well is the harmonic oscillator potential, which is the simply x squared times the prefactor. So the Hamiltonian of such a harmonic oscillator is very simple, because you know that in classical mechanics, so for example, you know very well that if you attach the classical object by a string or spring attached to the wall, and you pull that object, and the object will actually oscillate back and forth with respect to this equilibrium position. It's called harmonic oscillation, right? And you know the solution. So quantum mechanically, we'd like to solve this potential well problem, harmonic oscillator problem. So there are two ways to solve this harmonic oscillator problem. So first is called the brute force way. Directly solve the Schrödinger equation, and which is the way that we introduce at the end of this chapter. And the second way is to define an operator called the raising and lowering operator, and a dagger, or a dagger A, which will be introduced in the next chapter. And this is the much smarter way to solve the harmonic oscillator problem. So without actually involving this very complicated, say, polynomial and so on. Okay, so let's just do it more stupid way, which is the brute force way. Let me just write down this time-independent Schrödinger equation. Okay, so we like to solve the solution, find the solutions from the Schrödinger equation. So what do we do? Well, so we simplify the notation. So we defined, like what we did for the classical harmonic oscillator problem, we define these dimensionless variables like this, omega, epsilon, and y. So then we plug in this new definition of this dimensionless variables, we get this dimensionless Schrödinger equations. Okay? So then we start from here, and we try to solve this nonlinear partial, second-order partial differential equations, which is a bit complicated to do. So let's take a short break. When we come back, we will start to play some tricks and to solve this equation in this different limits. Okay, so let's try to solve this harmonic oscillator problem. So, of course, we don't have a very good guess or starting point, but there's some limits that we could consider to simplify the calculation. The first limit is when y is very, very large. So remember, y is what? Epsilon and omega. So let's look at this limit when this y goes very large, which means that this x goes very large. In this far away positions of x relative to this origin, and the solution is really, really simple. So let's just look at this extreme limit. So in that region, this y, when y is really, really large compared to this epsilon, so we can forget about this epsilon for the moment, and we just talk about this minus y squared, the second term here. So, and I call this solution u0. This corresponds to this solution when y goes to infinity. And this equation could be solved, okay, approximately. Okay, so let's try to solve this. And the way to solve this is to rearrange this term. So let me just skip some details. You could check your textbooks. So you could make a total derivative of this function with respect to y, and on the right hand side of the equation is given by this minus 2y u0 squared, and you carry out this differentiation and you go back to this original differential equation. So these two equations are identical, but when we do so, and we actually have the benefit, because this is the total derivative, right? And you could integrate this total derivative and you get some constant when you do so. So let's just try to solve this problem. So in this regime when y goes to infinity, and we further assume that this term, say the total derivative of y squared times u0 squared is much larger than this 2y u0 squared. So this is a further assumption of approximation. So we will come back to this to justify this assumption, but let's just take this assumption. So, and you could simply just ignore this term in that limit. So let's just try to simplify this equation as much as possible and see how it goes, right? So maybe this assumption is wrong, but let's just do it in any case, right? And see what happens. So when this term dominated over the right-hand side of the equation, and I can simply just ignore this right-hand side of the equation, and so the full differential equation becomes a very easy to be solved, which is the total derivative of a function minus y squared u0 squared, which is approximately given by 0. So you could very easily solve this differential equation because this is the total derivative of some function, and if you integrate over this equation on both sides, you get a solution. Okay, so you immediately find that du0 dy is given by what? Square root of constant squared plus y squared u0 squared. And in the limit of y goes to infinity, we know very well that in the very far away place, and all this Schrödinger wave functions should vanish, right? So u0 must go to 0. So it's the first derivative of u0 with respect to y, and which corresponds to this infinite potential well problem. So remember, when x goes to infinity or y goes to infinity, the height of the potential well goes to infinity. And so in that limit, this problem is almost the same as infinite potential well problem that we already discussed. So for the infinite potential well, so right at the boundary, all this eigenfunctions vanishes, so it's the first derivative vanishes there. So in this limit, we immediately see that this prefactor, the constant prefactor, vanishes. So simple. Okay, so then you could immediately get the solutions in this limit, where the u0 is given by e to the minus y squared over 2. Okay, so this is just the approximation when y or x goes to very, very large value. So let's just check whether this solution satisfies this assumption that we made earlier. So let's just check So if you check this, you'll find that the y0 u0 squared, the y magnitude is plus 2y cubed e to the minus y squared, which is indeed very large value compared to this. Okay? So if you take this solution from this approximation assumption, and you indeed find that this satisfies this approximation assumption that we made earlier, that this quantity should be much larger than that on the right. So it's checked, which justifies that this solution is a reasonable solution when y goes to very large. Okay, but what is the general solution when y is not that large? Okay, so when y is less than smaller than infinity in the finite range, we need to make a further assumption or a starting point. So what is the general solution? U of y, both in y goes to infinity limit and when y becomes finite. So to that regard, so we could again take our educated guess to assume that this general solution u of y is given by this limiting solution e to the minus y squared over 2 times some function h of y, and this function h of y, we don't know, and we need to know. We will know that later. Okay, so but if we are lucky, so when y goes to infinity, then this u of y simply goes to u0 of y. When y goes to 0, on the other hand, this general solution u of y reduced to the h function. So that's our hope. We don't know whether this hope is really working or not, but let's just take these answers, right? So we do have the freedom to assume any form of the final solution as long as we really find that out, right? As long as we can solve the h function, and it's our choice. Okay, good. So let's just try to solve the h function. Okay, again, so we take these answers and we plug in to the Schrödinger equation, and let's just see what happens when y goes to 0 limit. So if you are in this limit when y goes 0, and assuming that this u of y is approximately given by this h function, okay, which makes sense because when y goes 0, this exponential function e to the minus y squared over 2 is simply just 1, because e to 0 or minus 0 is 1. Okay, so you actually reduce, this u of y reduces to h of y, right? But what is h function? Well, you simply just plug in this solution and try to find this out. So suppose I plug in this h of y back to the Schrödinger equation over there, and this is something that I will get. So of course h of y could be any arbitrary function of y, but without loss of any generality, so this could be a polynomial of y. There's an infinite number of terms in this polynomial in y. So of course we could use such a polynomial to really say approximate this h function, but the question is what are those values of a of n? It's the same, right? So again, so this is another guess. Okay, so when y goes to 0, you could assume that this polynomial could be a good way to express this h of y. So you plug in this polynomial assumption of h of y back to this equation for h function. So if you do so, and you will get the following relations. You get a recursive relation between this coefficient in front of the polynomial of y, am, and am plus 2. Okay, so this is the relation will become very useful later, right? So it relates this prefactor, the coefficient am, to am plus 2. Okay, so you can see very clearly that we could separate this coefficient in terms of an even number of terms in even power of a polynomial in y and odd power in y. Okay, so you simply just can see that the even odd parity symmetry. So for even, you start from a0 and you may get a2 and a4 and so on up to a to m. For a odd, you start from a1 and you may get a3, a5 up to a2m plus 1. So this even odd parity symmetry reflects the symmetry that we can see from this potential. Okay, so the potential shows exactly this parity symmetry, and so the eigenfunction, the eigensolutions, must show such a even odd symmetry. And so the even and odd solutions are not mixed up, so they are independent. So this is because of the parity symmetry. Okay, so then the next job is to find out what this coefficient am are, and then we could have some recursive relations in the high powers of y, and then we could actually play some mathematical manipulations of such a polynomial for the high powers, and we make it the exponential function, and then we could use further argument to argue that this number of terms cannot be infinity. Okay, so m cannot be infinity. So m must be a finite number. And when we find out this m must be finite, and which means that we need to actually truncate or simply just cut off this infinite number of terms to a finite number of terms in this polynomial. Okay, and this tells us that up to some point when this polynomial ends, this coefficient must be 0, and this is precisely the condition to quantize the eigenenergy of a harmonic oscillator. So we will come back to this point later, but maybe we don't have much time left today, so perhaps we could just stop here right now. So let me just summarize. So this quantum tunneling phenomena is real, and it is the foundation of the STM technique. And virtual state is a very important concept in quantum mechanics, which has allowed us to really resolve this seemingly paradoxical statement or inconsistency between our understanding and this quantum mechanical strange phenomena. And finally, the harmonic oscillator problem, we try to solve halfway through this brute force approach that we directly solve the Schrödinger equation for this. Okay, so we will finish this section tomorrow, and then we will continue to chapter 5 and chapter 6, which is the starting point of the Dirac quantum mechanics. Okay, so or linear algebra, the operator approach of quantum mechanics. And we will introduce these operator methods in quantum mechanics based on this linear algebra, and Dirac notation. Okay, so if you have time, please take a preview of this chapter 5 and chapter 6, especially chapter 5. We already mentioned much of this, the general structure of the wave mechanics. You can take a look. Okay, so and this is the starting point of quantum mechanics. Okay, so far we just take a review, but with a deeper understanding of the principles of quantum mechanics in this concrete examples of potential problems. Okay, so that's it for today, and I'll see you tomorrow.